Hey everybody, well I'm back with my follow-up video on the EX controller, this time with the servo motors. I just did a video a couple weeks ago with the new AVID EX controller system that's based on the Acorn board. That was with the steppers, and I covered a lot of stuff there because the software was new and the hardware is new. This one I'm just going to cover the differences from that to the servos. So the previous one was comparing, Mach 4 to CNC12 and the control hardware to the previous ESS board box and everything. This we're just going to talk about the stepper or the servos themselves and changes in the software and tunability for the servos and stuff. So the upgrade was pretty easy. It was straightforward, I should say. It takes a lot longer. So if you do just the stepper kit, you're really talking about the box, and I mentioned the tool touch off. With the servo kit, you're replacing all the motors, all the wiring, and probably the most important or most time-consuming part is the Z-axis, because not only are you replacing the motor at the top, but down in the bottom of the original one with steppers, the stepper motor has quite a bit of drag itself, so not much more is needed to keep the thing from settling when it's powered down. So they just have a kind of, it's a damper or a little bit of a frictional drag device at the bottom of that. With the servos, when they're not powered, they just roll really easily. Like you can roll this gantry back and forth really easily. So they actually have a brake now with this, so you install that in there and the wiring comes up to here, and so the brake is on by default, and then when the system powers up and enables the motor, it shuts the brake off when it's going to move. So you actually have to take the directions show to take it all off and take it all apart and everything. So it's not hard. It just takes, I would say, probably took me somewhere between 6 to 8 hours one late night to upgrade the servo part. So not too bad. It went perfectly smoothly, other than one set screw that I had seized on that damper that I'd cut out with a Dremel. But other than that, everything went perfectly. So just wanted to show you, one of the cool things is these things are just super smooth. Very quiet. I don't know if you can hear it. With the jogging, they're just much quieter than the stepper. You don't hear those discrete steps and the frequency from that. You just hear mostly bearing noise and gear noise from the rack and pinion. They can run a lot faster, and we'll go over some of the settings in the software where AVID has a different motor speed default for the steppers versus the servos. The other thing is they do hard stop tuning, hard stop homing. So you still use the sensors, proximity sensors, to get it in the ballpark, but then it backs off and it converts over to the hard stop homing. So it essentially hard stops against the heavier duty stops that come with the servo kit. So it's much more accurate and reliable, or repeatable, I should say. I didn't measure the repeatability or anything like that, but everybody tells me that has measured it. It's a little bit better. And I didn't really have any problems with the original proximity sensors that AVID has on here. Also very repeatable. I would get probably better than 2/1000 of an inch repeatability, as far as I did a whole bunch of homes and then measure back to a location on my platform with a caliper or something. I always got very good results. So no complaints on the old one, to be honest. So I upgraded all of the Z, X, Y, and my rotary motor, and they're all done working. You do need new cables, and I'll go over some of the differences there. So I used my vibrometer, it's called. It's an app on here on my phone that uses the accelerometer. You can kind of see when you jiggle it. I don't know if you can see it on there, but It's pretty sensitive. It's not an absolute term, but I found it actually works pretty good. So I use this a lot on with Mach 4. So I know this basically this has a scale from 0 to 5, 5.5 or so. And I know that if I'm getting vibrations on this scale that are above 3.5, then I start to see poor results on laser lines, or I start to see kind of wiggly, chattery marks on things like V-carve walls and stuff like that. So my goal is always get the vibrations under 3.5 on this meter, whatever 3.5 is, I don't know. So we're going to see that, as I showed in the other video, the Centroid controller with the stepper motors was significantly better than Mach 4 with those same steppers. And then we're going to see that the servos are even better, and the servos are actually running faster. They're running a higher acceleration rate. I'll go over that too. So I did get better, more smoothness at higher speeds, and I know there's a lot more tuning that could be done to run these faster. AVID is actually pretty conservative, I think, in my opinion, with where they tuned this. Whereas on Mach 4, they shipped some of those with 50 inches per second squared acceleration. That was very jittery if you were going to try and do cars and short vector kind of work. And I usually had to detune that back to 15 or 20 inches per second square, for especially for laser work. Whereas on this, it's running 35 inches per second square, and I cranked up a couple of the different tunable parameters. I got pretty good performance increases and didn't really see any extra noise. So there's plenty of optimization that can be done yet for those who want to do it. Otherwise, the settings that AVID has this thing set to out of the box will beat Mach 4, and it will also be better than, much better performance-wise. I think it was about 15 to 20% speed improvement with better vibration yet, just with their out of the box settings. So if you don't want to mess with anything, which is, you know, obviously what AVID recommends, you will get better performance, and we'll go over that later. So let's get into some of the details of the motors themselves and the wiring and things like that.
All right, now if you remember on my previous video, I had this box flipped upside down because I just had it sitting on a cardboard box, and I wanted the cables going out that side because I had it actually over here. It was just more convenient to do the quick test. I kind of reset up my whole system here, where I've got my main controller now in the middle instead of up front, and I've got my laser box up front, and that was really just to get the cables to come out here instead of up at the front of my machine. I didn't want them up there where they could get kicked and damaged easily. So I do have my system right side up now, and so everything down here, the 48 volt supplies, the Acorn, some of the power supplies and contactor, those are all in exactly the same place as they were in the stepper version of the control box. Still has the same interface board. As far as I know, it's the same board. I didn't look at it close enough. It's possible that they have a different version. I didn't ask, and I didn't look at it close enough. But you'll see a big hole up here where all the stepper drivers were for my other box. So because they're servos, the driver is actually up here in the motor. So that basically left a big hole here, which is really cool because look at that, there's a DIN rail, and I can put like a 12 volt power supply, an extra power supply in here to run, say, my dust shoe light and my laser crosshair and stuff like that. I don't really want to tap in and use the power that's allocated for the Acorn and stuff like that. I'd rather just put another power supply in there. So I'm going to do that in the future. But that's kind of cool. There's a little bit of space left over in there for that.
All right, let's look at the motors themselves. So this motor is the bigger sized one. So they have X and the 2 Ys are a big motor. Whereas on the stepper system, the NEMA 34s or the NEMA 23s, they're all the same size. These are Centroid, or the Clearpaths come with quite a few different sizes. They put the bigger ones obviously on the Y and the X. If you look at the rotary unit, that's a little bit shorter. It just doesn't need that much torque. And the same with the Z-axis, it doesn't need as big a motor either. So one of the things you'll notice here is there's a little blinking light under this cover. You can pull this off and see there's a little USB port in there. So these are real smart motors. They have this heatsink back here is for cooling the driver. So there's a whole electronics package in here besides the motor that's in here. On a stepper motor, it's a dumb open loop motor, right? You have a step command, which is just a pulse to tell it to take a step. You have a direction signal that's either high or low, and it's just telling it, are you going forward or reverse when you step? And then there's a enable signal. These stepper motor or servo motors don't work that way. They are basically commanded by a controller to go until the feedback says to stop. And so the feedback is coming back from an encoder that's built in. So inside of here, there's an encoder that has, I believe on these motors, it's 12,800 steps of resolution, which the motor itself is only commanded, I believe, 2,000 steps. So it has a lot more resolution on the feedback, which you want. So that's how it holds position. And I should say, these motors are actually made to work like stepper motors in that their interface still has the step, the direction, and the enable signal, but they have a fourth feedback signal that you can use for alarms and errors and stuff like that, because it does have the smarts in it to know when there's an error or something. So even though it's acting like a stepper motor as far as the CNC controller goes, inside it's not a stepper motor. You give it a step and it moves to that distance, and then the controller in here is looking at the position from the encoder and holding it forward and back, and you can actually hear it move. If I push on this axis, I don't know if that comes through. Let me put the microphone on the motor here. So I'm pushing against it now, and you can, hopefully it's coming through. You can hear the motor pushing back against me, trying to adjust and hold that position. So that's how they work. They're constantly watching that encoder, trying to maintain the position they're on, and that's why they don't lose steps. If you push them out of a line a little bit, or they run into something a little bit, they will try to correct themselves, and they will be able to correct it as long as you don't do anything too drastic. Like if you run your Z stage down into your spoil board hard enough and long enough, it will throw an error. You'll get an axis error. But if you just go down and bang it and come back up, where the steppers would have for sure lost a couple of steps, and you wouldn't probably even know it, and then you didn't rehome because you didn't know it, now you've got an error. These are either going to correct themselves if they didn't go too far, or it's going to throw an error back to the CNC12 software, and you'll get an axis error. And I've done both of those, so it's kind of nice. It's either going to self-correct or let you know you better go home again. So because these have a controller in it, you got a signal cable bundle here that has your step, your direction, your enable, and the feedback. That's this wider connector, and then you've got a power connector. So these normally on a stepper, you have the stepper's drivers were in the control box, and so you put 48 volts right to the driver right there, and then those signals that I just mentioned went straight to the stepper driver inside the control box from the Acorn or the ESS board. Now you're actually running those signals all the way out to the motor itself. So that means each one of these motors has two wires. It has a 48 volt power connection, and it has a signal connection. You can see on the back of the gantry, this is my power distribution box. So you bring 48 volts up from the power supplies. So this wire goes back to the control box, and it basically just fans out the two Y motors, the Z and the X, and then there's a separate connection for my rotary. But so you're feeding out 48 volt power to all those motors, and then the signal wires for controls are just separately routed, just like the wires used to be for the stepper motors. So that's basically the difference. These motors are much more sophisticated, and the other cool thing that is in these is they're self-tunable. They got a software program. You plug your computer with an application into the USB port, and you can tune these. Now you don't have to do that. Avid's already done this basically, but if you go online, if you're curious, you go on YouTube and look at like James at Cloud 42. He built an Avid machine and put steppers on himself a couple years ago, and goes through the tuning process. But it's really cool. You weight your system down so it has, all the mass that you plan to have on there, and it goes through a tuning process. And what it does basically is it calculates the acceleration profiles that give you the best performance. And the reason it can do that is because it's got that really fine-grained resolution on those encoders to see how the motor and all this mass respond to some stimulus that it's commanded. So basically it goes through this training routine, moving back and forth, slow, fast, big moves, small moves, and it's learning how the system responds to the inputs. And then once it's all done, it basically knows the best way to move the axis to get the least amount of vibration and the best accuracy. And so you don't have to do that. Like I said, Avid's done that based on, the spindles, the laser being on there, all the weight, the size of the gantries. It's kind of interesting when you get these motors, they're all labeled like you see here. This one says Y. That's because the Y motors have different tuning parameters loaded in the memory in these than, say, the X or the Z's or the rotaries. So you have to use those in the same spot, even though they might be the same physical motor. They're programmed differently. Like I said, Avid's already done that, and they don't recommend you mess with it, and I don't recommend you mess with it either. It's quite a bit of work to do that, and from what I've seen, they work really good, and we'll go over that in a bit. These motors bolt right onto the drive hardware. Very easy to do. It's all kind of the same as the steppers were. So that's the motors in a nutshell. They can go faster. They don't lose steps. They're much smoother because of the built-in actual smoothing control in their drive algorithm. So my goal here is to show that there's actually a performance improvement just due to the motors. So let's get into that. So I want to go over some of the software settings real quick, just to kind of give you an idea of the difference. I didn't go over this in the previous video. A lot of it had to do with I really only had maybe 10 hours on the system when I did the first video. I've learned quite a bit since then looking at the steppers. So if we go to the main menu and we go into the utility menu and the advanced configuration and then into the machine configuration, you've got a bunch of different things here. One of them is the jogging menu. So this one has a lot of the motor parameters that are important for setup. So the first thing, obviously, here you can see there's just plain jogging parameters. So you can set each axis for its low speed jog. So this first column is when you're in low speed jog mode, here's the speeds they're going to run. And then you got fast jogs. And one of the really cool things that Centroid does is they give you the ability to set a negative or a positive jog at a different speed. And normally you wouldn't care, but on the Z axis, you can see here, we've got 150 for the negative, but 500 for the positive. And the reason is, generally, if you're plunging, you probably don't want to do a fast jog and jam your bit into the workpiece. And so it's kind of nice to have it only allow you to go so fast when you're going down. So if you accidentally rotate your dial on your pendant, you won't quite as quickly jam it in there. So that's kind of nice. They have
parameter here called max rate. Now, that's similar to what was on Mach 4. It also had a max rate. So this is the maximum speed you can run doing anything. You can't jog faster than this. You can't run your you can't run your override past that speed. You can't run a feed rate or a rapid past that. That's your max cap, just like it was in Mach 4. But the difference there is that also affects your acceleration, because instead of just a straight acceleration value in some other parameter, they actually have an acceleration time set, and it's in a different menu, and I'm not going to go over that where it is and stuff, because they don't recommend that you play with that, but it's set to 0.5. So what it means is it will accelerate to full speed in a half a second. And so that means your acceleration is your max rate divided in, this is in inches per minute, so it's inches per minute, and you divide that by 60 to get it into seconds. So it's 1,000 divided by 60, and then it's divided by a half, and that gives you inches per second squared, which is your acceleration. So the equivalent here, this 1,000 is 33.3 inches per second squared. So that would be, what you're comparing to on Mach 4, for example. The interesting thing is here, AVID sets all of these parameters the same, except for these, for the servo motor, because it can handle the higher acceleration rate, it can handle the higher speeds easily. And from what I've seen, they're actually, like I said, they're conservative with this. They'll actually run a lot faster. But this is kind of where one of the best places to set your acceleration. So even if your feed rates and your jog rates, like you can see my jog rates, I'm not going 1,000 inches per minute. That's where AVID set it. I don't like it running that fast, so I'm only jogging at 600, but my max rate is still up here, so that's keeping my acceleration rate up. If you look at the stepper motor setting for this, AVID sets this at 600, and that math turns out to be 20 inches per second squared. So 20 inches per second squared is what you get with the EX system on steppers. If you compare that to how it was under Mach 4 for AVID systems, they usually defaulted to 50 inches per second squared with a lot of their configurations. Some of them were lower, but what I always found with V carving, 3D carving, and especially laser work, I actually had to go down to 15 or 20 to get the vibrations under control enough to really get good cutting results. So yeah, again, as I've mentioned in other videos, it just depends on whether you're doing, cutting out big sheets of plywood for cabinet carcasses, or if you're doing laser work, and it kind of depends on what you need. So what's cool here is we're going to see is that we already saw a smoother performance with the steppers, and now we're actually cranking up the acceleration to 33 inches per second squared, and we're going to actually see that the vibration with the servo motors is actually still much lower than it was with the steppers at only 20 inches per second squared. So there's some other parameters in here that you can actually do some speed tuning with. It's fairly advanced, and I'm not going to recommend you go messing with those. If you are in, AVID recommends don't play with those. There are some Centroid forums where the experts kind of help guide people through that. I've played with a few of these, and what I am going to say is there is a lot of extra performance in the system where you could really speed things up and still get good vibration performance if you wanted to. And I plan to do that in the future, but I'm much too much of a novice right now in the system to even think about doing a video on that yet. So, but like I said, I've been real happy with the performance that's sitting on the table that we might be able to get in the future. But like I said, out of the box, this thing is already performing very well. So that's really it. All the other Centroid features really don't care about which motor is in there. AVID's configuration in their wizard pretty much handles setting all this up for you, whether you pick servos or stepper motors. So
you really don't have to go in here and mess with any of this stuff to make it work. In fact, when once I installed my motors, I only had to go in there into the wizard and click a couple different things, and I was up and running with the servos. So very good. Now because the vibrations got low enough with the servos. Actually, they got low enough already with the steppers under CNC12. So the glass with the liquid in it was not as useful because the vibrations were already so low with the stepper and the CNC12 and Acorn that it almost didn't show any surface disturbance. So on this servo round, I'm just going to rely on the accelerometer meter to give us some relative measurements. And again, I'm looking for basically to stay under 3 or so on that scale. And if I'm there, I got very good vibration performance. One other thing I wanted to point out, I mentioned smoothing on the original video. I didn't fully understand that at the time. I still have a lot of learning to do, but I got a much better picture thanks to CNC Keith and one of his software engineers for helping explain some of it. And again, Centroid has awesome documentation, so I've just been reading through a lot of that over and over to kind of let it soak in. But they have smoothing and they have motor tuning. So everybody has motor tuning, right? Like the acceleration I mentioned. They've got some of these parameters, and there's a few other ones in some more advanced menus. These are directly adjusting how the motion control works in the hardware. So down in the Acorn, how does it go around corners? How does it stop and restart and accelerate? What's its max speed? Things like that. They will affect all of your tool paths to some degree or another. So for example, if you have a tool path like my good vibrations test, that's a whole bunch of super tiny little vectors. It's because it's text, super tiny text. So it's basically running in the acceleration zone all the time. It never gets, I have the file set to 100 inches per minute, and I don't hardly ever see it go over 20 on the display when it's running, because it's just starting and stopping all the time. So on something like that, acceleration really kicks in big. Some of these other parameters here will also make a pretty big difference. But on my other test where I have the simple shapes, I've got circles, squares, a star, and a simple oval. Those don't have a lot of turns, vector transitions. Like a square has 4 straight lines, so 4 vectors. A circle has 4 arcs in it. So you don't have a lot of transitions, and you get up to speed and you just run at speed. So in those cases, a lot of this tuning doesn't really matter, and the overall execution time mostly is dictated by your runtime, your feed rate. And then you have some, combinations of each in there. So then if we go back and look at what is smoothing, they have this whole, one more menu. They have this whole smoothing thing here. And I mentioned this before. They've got these presets, which are really nice. If you go into one of these, they have all these smoothing parameters, steps and minimum angle, S-curve. This is all stuff that CNC12 pre-processes on the G-code before it sends to the Acorn. So think of it as, it's basically the equivalent in Mach 4 of constant velocity mode, where you could mess with, there was a couple of data tables there where you could say, well, on this kind of an angle, break that up into multiple steps. Essentially, it's going to turn it into, instead of like a square corner, it could be turned into a rounded corner, and you can tell it how much tolerance or error do you want. And that's what you can do with all these. Only these have way more capability and more adjustability, but they're doing the same thing. It's adjusting the G code up front before it goes down to the Acorn, where all those motor parameters kick in down in the Acorn. And I have not been able to see much difference with these, but I haven't spent much time.
don't affect any of the 3 G-code files that I have. They don't affect them for runtime speed. Um, and I know on the previous video I showed it actually improved it on one. That was an anomaly, and I'm going to talk about that when we get to performance. That was an error of some part of mine. I don't know how it happened, but however, I have seen quite a bit of discussion on the forum about these for specific kinds of tool paths. So they've got some optimized ones in here for, like, if you think about some of the 3D carving where you got these large arcs, like say you're trying to make a bowling ball on your rotary unit or something, you know, you got an 8-inch diameter circle or something you're trying to carve. In some cases you'll see like the transition between vectors on those they'll actually show up when you look at them, you can see that vector transition because the tool path isn't done very good by your cam package. And so if you got a really good cam package, smoothing isn't needed because you already got good G-code. But if you got a really raggedy G-code where it's trying to make some profile, like for example, I see this if you do ovals in Vectric, there's a lot of little vectors there on the kind of the sloped edges, and they can end up kind of jaggedy. The smoothing can help fix those if they're poorly done in the first place. But if you got really good G-code, it doesn't have much to fix. It's already smoothed out, right? So that's the purpose of these. These are kind of a high-end cleaning up of the G-code itself. They do have a downside. They can generate a lot more commands going down to the Acorn, so it can load up your PC with a lot more CPU load if you really go crazy with how much stuff you have it doing here. But for the most part, like for laser work, I mentioned in the last video that I was doing laser smoothing. That's actually a term that AVID used in their wizard for one setting there. It's called laser smoothing. What they really mean is whether or not they're allowing you to use the smoothing at all here. They actually turn it off. They recommend turning it off in the wizard, and it's essentially using exact stop mode, except for it's turning off one other thing that speeds it up. And honestly, I'm getting great results on the laser with no smoothing. It just doesn't need it. I've run some very small text. This text is actually my XT50 laser, so that's a 2,000th of an inch laser beam, and it's writing extremely small text. I have to look, if I look at this under a 30x magnification, it's very smooth. There's no vibration on this. I've got this cranked up to 100 inches per second. As I mentioned, it really only ever gets to about 20 inches per second on any one of these things because they're super, super tiny. But it blasts right through that very smoothly, very, very crisp letters with just the default setting in exact stop. So AVID did a cool thing with the laser is they sort of built it in with the spindle. So they made it a special tool number. And so you can go from spindle to laser to spindle just with tool changes in the file. And so they take care of setting all the laser parameters in the background with macros. It's pretty cool. The other thing is you don't need any special post processors for that because the laser only commands are done before it gets to the G-code file in macros. So the same post processor can do spindle stuff as well as laser, and it can put both of them in there and just handle it with a simple tool change. So they also handle the laser to spindle offset in X and Y and the Z difference. So it's a pretty slick system as far as integration, I think. But again, I just wanted to reiterate this would have to run very slow in Mach 4, probably 10 or 15 inches per second squared to get this quality. So in this system, I've got it set up to 33, and like I said, I've run it faster and still had it really good performance.
All right, let's take some look at performance here. First, I want to start with just the raw pictures. So with the servos in here, this is my shapes test that I've been using to kind of judge the quality of the movement itself, because this is a 2/1000 of an inch wide laser. It's very thin line, and any bad vibration shows up in here pretty well. So this with the servo again is 35 inches per second squared acceleration setting. I'm not running any smoothing with this. This is just, it's not exactly exact stop mode, because there's a command called M64 that turns off the stop part. So it basically goes from vector to vector without coming to a full stop. But it doesn't do any rounding or anything like smoothing does. You get very good results here. So if you look at this little squiggly on the left side of the middle oval, that was there on every single run. So that's, I think that has something to do with the resonance in my machine for that specific movement. I saw it on all of them. For some reason, it's only in that one exact spot, and it has that same frequency. But everywhere else you can see, there's very sharp corners everywhere. There's very little squiggling, like when it bangs around these corners in the square. Look how tight this square is. Again, these are 2/1000 of an inch wide, so these are very small objects that I've zoomed way in on. So with some of the smoothing turned on, or the equivalent in Mach 4, the constant velocity mode, you start seeing some of these edges get rounded off, and it just doesn't do that. The runtime is about equivalent. It's slightly slower on this than I was getting in Mach 4, but it's pretty close. There's the part of the problem is, like with this particular toolpath, there's a whole bunch of Z movements that happen right now before it gets to the actual burning of the code, and so I'm not sure how accurately I subtracted that off. It's in the G code and some of the macros that Avid's written. So the Z goes up and down full distance, and on mine, that's on my Z axis, that's like 12 inches. So there's some time burned in there. So I think these are basically equivalent runtime. The other thing I should show here is the CNC12 has what they call G37. G37 is called velocity modulation. So what that does is, as the speed is slowing down at the end of the vector, it proportionally cuts back the PWM power with the velocity so that you don't get overburning. So I turned it off here, and you can see between each arc here, you can see how dark it is. So the speed, the axis is slowing down here, and the power is staying constant, so you get a much heavier, deeper burn. You can see, like on the ovals here, where these ovals are made up of many, many, many tiny little segments. So they're constantly speeding. So they're not getting anywhere close in this region to full speed. So that's basically just like it is this transition between the two arcs here. You can see it's a lot darker because it's basically at full power. Whereas on this one, G37 is on, and you can see there's no burning in the corners where it's slowing down. So the proportional control of that PWM signal is very good on Centroid as well, just like it was on Mach 4. So you don't have to, you see a lot of people with crappier controllers on their lasers where they have really spotty effects and corners, overburning and stuff. You won't have that with this. So very pleased with these laser results. This is very clean, smooth laser cutting here, or laser etching in this case. I'm not cutting all the way through. All right, well, let's go into the runtime performance here. This is my chart for vibration and for just execution time. So if you remember, I used that shapes routine that I didn't run the vibration meter on that, I was mainly looking, that one I didn't need the vibration meter because the quality of the image itself tells you everything you need to know. But I did want to try run time, execution time. Again, the good vibrations is the is a very small text. It's actually about 60 thousandths of an inch tall, and it's a double line character. I'll show a picture of that later, but it's pretty impressive how this thing can burn that. And that one, I didn't turn the laser on and look at the quality for the most part. I was just looking at the vibration meter and the execution time. And then the 3D carve is a sliver of a very large 3D carve I had, but I took the area where it was banging the Z-axis up and down the most, a real steep transition in depth of about 3/4 of an inch or more. So those are the same exact G-code files that I used for Mach 4 on the EX with steppers and the EX with Clearpath. So I did have one thing I wanted to clarify. This one here, that was some kind of an anomaly. This 11 minutes and 25 seconds was not correct. I don't know what happened on that run. It just couldn't have been that slow. So I got my hopes up a little bit too high for the smoothing there. This is the reality. So if we look at 3D carves, I did it under both acceleration values in Mach 4, and then what I did was there's not an apples to apples. So what I did was the pseudo exec stop mode at which is this one right here, and then I did the 3D relief carving smoothing algorithm on this line. And so what you see here is that under Mach 4 at 50 inches per second squared, which is kind of their factory setting for my machine, I'm getting the vibration range from 3.5 to 5.5, and I colored it red because these are totally unacceptable numbers. You get all kinds of, the laser will look bad, any V carving will look bad with this kind of thing. But the execution time was pretty good here, 18 minutes. Then when we went to the steppers again with the EX controller, it's about in the same ballpark, but if you remember, the steppers were running only 20 inches per second squared, so you would expect these to be slower than these. However, it's not much slower, considering now but notice how the vibration range is only 1 to 3, whereas it was 3.5 to 5.5 here. So we're slightly slower with the steppers, but significantly better vibration. This is a totally acceptable vibration range. Now when we go to the servers, we drop down from 19 minutes 2 seconds to 17. So we lose we speed it up by about 5% here. But now look, we even dropped even further on the vibration. Now it's 0.5 to 2.5. At this point, any liquid in a glass is basically not visibly jiggling at all. That's why I didn't even bother filming these after I tried this. It wasn't even a useful metric anymore. And I ran up here the smoothing routine. It actually was a hair rougher. It tightens it up so you don't get the very low values. The peaks aren't any worse. Same exact execution time. Same, and in this case with the steppers, it was the same exact smoothness. So it got a little bit better smoothness with the steppers, but the servos were just so smooth that even, again, this is faster, quite a bit more acceleration than this. And now, though, the 17 minutes beats the exact stop of the Mach 4 running at the really fast. So you're running faster and way smoother. And I think, as I mentioned, you could improve this time quite a bit with some more tuning, because you could, realistically, you could sacrifice some of this and move it up into the 3.5 range, and you'd still, you know, not notice cut quality go down as long as you kept it to maybe under 3.5. So the stepper or the servos definitely have an advantage here of running faster and yet still smoother. So if we go up here to the good vibrations, same thing here. We were 8 minutes 5 seconds on the acceptable Mach 4 performance. Again, if I run it 50 inches per second square, we're up 2.5 all the way to 6. This one literally shakes my workbench that's, you know, 10 feet away from my CNC through the concrete floor. This is totally unusable vibration. But when we went to the EX system with the steppers, we got all the way down to a 1 to 3.5 range, and yet we saved quite a bit of time here. A minute and a half time savings out of 8 minutes. So, you know, that's a 10-15% improvement. Then we go to the servos, which are running yet more acceleration. You can see my top end vibration went from 3.5 down to 3. So it's about the same range, but slightly better, but significantly faster. So again, a marked performance improvement, both in runtime and vibration. Then on the shapes, these don't, as I mentioned before, these have a lot of, they're more longer vectors. It's a very short file anyway. So it's about the same as, again, these have some overhead, especially large compared to the Mach 4 run overhead with my spindle going up and down in here. And that's just something I need to go clean up in my post processor and Vectric, but I would call them about the same. I didn't subtract off all of that overhead of the axis moving around before it gets cutting, but we already went over the pictures. I mean, there's no comparison to the pictures of Mach 4 running here. This is just all jaggedy, not very good. Whereas both of these, when we look at those pictures, they're just excellent. There's no signs of vibration there or anything, even on very, very small features that you have to look at the microscope to see. So just for fun, I did turn the laser on one time after I got the servo stuff working on the good vibrations tests. And so here you can see the quality of this text under 30x microscope, or it's actually just a jeweler's loupe, but 30x magnification. So these characters, text characters, are only 60 thousandths of an inch tall, and it's actually a double laser line. You can kind of see it's a double vector font, and it's, I mean, again, I've got this running at 33 inches per second squared acceleration, 100 inches per second, 100 inches per minute feed rate. Obviously, it's not actually hitting that because it's so tight, but this is just phenomenal quality at this size, not to have vibrations and stuff in here on a really big CNC router, you know, that tends to vibrate. So really impressed with this.
One thing I mentioned briefly but didn't say much about yet was the fact that on the EX controller, AVID has moved the two utility relays out of the control box. It was getting a little cramped in there, and I think they wanted to make it a little more modular. So now what they did is they put a M12 jack for a cable that supports two relay control lines, and then they've made this nice little modular box here. So you get a plug, basically two 30-amp relays in here, the connection to control it, a little hardware kit here to just basically mount it anywhere you want on the machine, and then the M12 cable. So you know, it still uses a couple of control bits or outputs from the control box to run this. The cool thing is you can rewire this easily, that the lids come off. You notice I got a different color screw here, because if you do take these off to change them,
when you tighten them up, they should be snug, not really tight. They snap off pretty easy. But this is a really nice little box. Like I said, two 30 amp double pull relays in there, and you can get it in two 120s, two 220s, or in my case, I have a 120 and a 220 plug here. So you've got the input wires, which are, I didn't measure them, they're got to be at least 10 or 15 feet long, and then your two switched outputs here. So nice little kit. I think it's a little more, quite a bit more flexible, obviously, than the other setup. You can move it out, you know, towards the back of your machine or somewhere where it's more convenient that way. And this cable is really long, so you could literally mount it out in your wall by your dust collector or something. It wouldn't have to be mounted to your machine frame. But nice little addition to the new EX kit. Okay, so kind of came to the end here. I guess to say about both of the EX kits, the servo and the stepper versions, they both have very good instructions from AVID. They're both easy to install. The servo one obviously takes more time and effort just because there's a lot more wiring and swap out of components involved, whereas the EX stepper kit is just really adding the touch plate and the swapping out the boxes. Lots of people, one of the main reasons for this video really was to help people decide, should I buy the motors, the servos, or the steppers when they're buying a new machine? Or if I already have a machine, should I upgrade to the EX kit with stepper and keep my steppers, or should I go all the way and get the servos as well? I think if you're buying a new machine, for almost anybody, I would just get the steppers as well. They make a pretty significant improvement in performance, and when you're starting from scratch, the cost isn't really that much different. And obviously, you need the EX controller anyway, because that's all AVID is selling. So that's pretty easy. If you're upgrading, if you've got like a desktop Pro or something that's very stiff already, very rigid, and it does what you want to do, you know, you're using the spindle maybe, and you don't care if you're adding a laser, and you don't really care if you're going to keep up with AVID's future developments and stuff like that. And if Mach 4 isn't causing you fits with glitches and stuff like that, you know, some people had lots of problems with it and some people didn't really have any. If you're running okay with that and stuff, yeah, you don't need to upgrade either if it does what you want. If you're looking to get better, smoother performance, you know, keep up with AVID and their future developments, they're gonna be coming out with some cool stuff this year. And you know, you need the new controller to support it, because all of their software development going forward is going to be on the EX. Then you probably want to upgrade to the EX kit. I would say, especially if you're a professional and time is money, I would definitely recommend upgrading, just because the machine is going to be more reliable, I think, and you know, your runtime is going to be a little bit better for the same amount of performance. Then with the servos for the upgrade, you know, if you're a hobbyist and you don't care about time, you can always slow down the EX with the steppers and get good vibration performance so that you get nice clean laser lines and everything. But if you're somebody that really cares about time, again, if you're a professional using this machine, I think in any case, you're going to want the servos. Like if you're cutting out big panels, it can just run way faster. But if you're doing small detailed work like carvings and stuff like that, it can also run way faster and still give you even better vibration performance. And then if you're just a hobbyist or somebody like me that loves new technology and thinks the servos are really cool, well, I don't even have to tell you guys, because I know you already ordered your kit anyway and it's on the way, so you don't have to decide anymore. So that's it. I think I've covered all the main points. I got a lot of work to do with laser optimization. The EX does some really cool stuff with laser rastering right out of G-code instead of having to do a built-in raster routine like we did with Mach 4. But I haven't done enough of
of that yet to really talk about it much yet. There's a lot of other things like touch probe and probing stuff that's available in Centroid's CNC12 software that I haven't really played with yet. Lots of cool stuff coming. I know, like I said, AVID has a lot of new things I think they're working on. Centroid has a lot of stuff you can buy online that AVID isn't necessarily selling yet. So it's kind of a neat overall package, and so I'm looking forward to digging in deeper. I'll definitely be doing more videos on laser work, maybe some tuning things for performance, getting the runtime speed of the machine up a little bit. So if you have any questions about any of this, please throw them down in the comments, and I'll answer you right away. Thank you.